Welcome everyone to Astronomy State of the Art, another one of our live sessions. Hoping you have some questions to ask about astronomy or astrophysics, anywhere from the solar system to the universe itself. Well, ready for your questions.
Okay, here's our first question. I have just read on Yahoo about an asteroid of Manhattan size discovered by a NEOWISE telescope that might impact the Earth. Are we prepared to diffuse such threats?
It's a good question because the search for such objects has become very comprehensive, actually. So Manhattan-sized objects or objects in the range of around, a few kilometers in size, which are continent-destroying, if not civilization-destroying. Those are expected to be quite abundant, and there's a network of telescopes, one of which the question alluded to, but I think there are almost 20 telescopes around the world, roughly a meter in size, that can detect such objects. So it's important for the people who do this work to communicate and make their data public fairly quickly. And it's also important, given the implication and the fear factor, to be responsible about reporting the data and interpreting it. And that's really the trick. When an object like this is identified, as in the example given in the question, it's typically very far from the Earth, but on a potentially Earth-crossing orbit. So it's likely to be hundreds of millions of miles away at the time that it's first picked up. And that's important. We need an inventory of these objects when they're far away and might hit us rather than when they're so close there's no time to do anything about it. So for typical Earth-crossing trajectory, something originating from the asteroid belt that's coming inward, or a comet trajectory, the speed is such that they're detected with months of notice, sometimes even a couple of years of notice, or a couple of years to go before they would even potentially hit the Earth. So it's not like a movie scenario where the thing is picked up by the intrepid astronomers trying to save the Earth, and then it's like 24 hours like the TV show. There's a clock running in the corner and everyone's scrambling around and looking very much like movie stars and presidents in movies taking care of the business and saving the Earth. No, we're going to have a long time to work on it. And the other thing is that when the objects are picked up on a potentially Earth-crossing trajectory, the orbit is not calculated with a high degree of precision, and there are many possible paths that object could take, most of which, the vast majority of which, will miss the Earth. So it's never certain when an object is picked up that it's going to hit the Earth, or even that it's going to cross the Earth's orbit. And what happens is, when a potentially damaging object is picked up, then people get a little more active. They start measuring its orbit. These telescopes, of course, look at the whole sky to pick up everything, but they don't look at a particular piece of the sky more than every few nights, sometimes once a week. So when you find something potentially that is a problem, you start observing it every night, getting better data, more accurate data, and you crunch down the orbital parameters or measure the orbit with much better precision than the initial measurement. In virtually every case, that leads to a predicted orbit that misses the Earth comfortably. And that's almost always what happens, and we don't even hear about it because that work takes place without a press release or an article written about it. There is a NASA website that carries with it what's called the Torino scale. It was named after, I think, a conference that was held on Earth threats from asteroids some years ago. And the Torino scale is sort of an analogy to the Richter scale for earthquakes. It defines what the potential threat, not the nature of the damage from the impact, but the likelihood that the threat is real or will pan out. And on this NASA website, I can't remember the URL, but if you Google NASA and Torino scale, you'll certainly find it. It's a public website. It basically lists NASA's ongoing database on potentially Earth-crossing asteroids, and it assigns to each one, updated almost continually, a probability of impact in the Earth. And if that probability gets, I think, above 1 part in a million or a million, the scale changes from green, meaning no problem at all, to yellow, and then there's orange and there's red. And so it's a very interesting snapshot of this research to go to that website and check out the color coding and the probabilities of hundreds of objects that are being tracked. And even those are just the subset, could possibly cross the Earth. And you'll see, of course, that they're almost all green. Occasionally one goes yellow. But if you then look at the one that went yellow and go back a few weeks later, you'll almost always find that it's green again. And that's just because, it's not because the thing changed direction, it's because they calculated a better trajectory based on the potential threat, and it turned out that it was going to miss the Earth. So that's the scenario. And even as an object has a highly accurate path calculated and is approaching the Earth, it's still almost always the case that it's going to miss the Earth. So the odds of an impact are exceptionally small. We know they are because Earth sort of civilization-destroying impacts only happen about once every 100 million years. The odds of that happening in 1 year are 1 in 100 million, an incredibly small number, and that's what the statistics say. So we know that in a particular 10-year period with NASA data, you're just not going to pick up something that's going to kill us. So that's the big picture. Then to answer the question, what happened if we just get very unlucky and one of these does seem to be coming our way, and the calculation shows that it will, and improvements to the orbit continue to show that it will. You still have, depending on the nature of the orbit or the trajectory and the speed, which ranges from 20,000 to 100,000 miles an hour, months to a couple of years to do something. NASA has technologies, and working in harness with the U.S. military or the Russian military with big rockets. We have technologies that could be got off the ground pretty quickly, and certainly within a month or so if the threat were real, to send space probes, sort of massive space probes, in the direction of the object. As you've seen in the NASA space program, NASA has the ability to soft land on targets 1 billion kilometers from the Earth. Titan, that was the Huygens probe 10 years ago. So, and we've swooped, Cassini has swooped within 10 miles of distant objects in the Saturn system. The OSIRIS-REx mission is going to soft land on a comet, bring back material. So we know how to get really close to and even land on fast-moving objects in space. Not a problem. And in this case, the mission would be to send a space probe to the object and not obliterate it, sort of Dr. Strangelove scenario, but actually send the spacecraft alongside it, in parallel to it, and use what's called a gravity tractor, which is, without being connected at all, the mass of the spacecraft, acting even on the much larger mass of the asteroid or comet, will slightly deflect it in its trajectory. So that process, carried out for a period of months, substantially deviates the predicted trajectory of the object and takes it away from an Earth impact. That's this kind of sort of gentle, gravity-savvy way of doing it, and that's basically the plan that will be followed. In the extremely unlikely event that one of these potential impactors has our name written on it. A long answer, but it was an important question. We want to sleep at night, of course.
Okay, now Keith asks, it is said that the gravity from black holes is so strong that nothing can escape, not even light. When pictures of active black holes are shown, there are energy jets shooting out of the tops and the bottoms. That seems to be a contradiction. What's going on?
Right. Very good question. Black holes are supposed to be black, and yet we find black holes by emission coming off them or near them. What's going on with that? So what I'm going to say is true for all mass black holes. The small ones that are the remnants of massive stars when they die, or the vast ones like the one in the center of our galaxy or the center of other galaxies, which range up to billions of times the mass of the sun. In a pristine vacuum of space, we do believe that black holes are indeed black. Nothing can escape. The definition of a black hole is an object that's so compact that there is an imaginary surface, not a physical surface, called the event horizon, that demarcates the boundary between stuff that's trapped forever, information that's trapped forever, and the parts of the universe we can see. So you can think of the event horizon as it's an imaginary, as a mathematically defined surface that divides a region of space-time that we can have no knowledge of, and that's what black hole theory has always said. Beyond that, we can see. However, there are extreme distortions of space-time. Gravity is causing intense and strange effects near the event horizon. So the event horizon is in principle something that nothing can get out of, and so therefore a naked black hole should just look black. So with one caveat that I'll come back to, that's the classic theory of black holes. They are indeed black, and no radiation should come off them. But that's a black hole in a hypothetical situation of complete total vacuum, no matter nearby, nothing else going on, isolated in space. Most black holes, most of the black holes that we found are either in binary systems, because most stars are in binary systems, or they're in the center of galaxies if they're massive black holes. And the center of galaxies is a very crowded place. It's full of stars and gas. Stars with much higher densities than around the sun, maybe millions of times more dense than stars. So real black holes are very often in places where there is other matter, another star, gas, dust, whatever. And in that situation, they, of course, will exert gravity on the nearby object or the nearby matter. And as that matter swirls into the black hole, typically falling in along the equatorial trajectory in the equatorial plane. So remember that a black hole is an initially large and mildly rotating object that is collapsed by a large factor, maybe a factor of millions. And by angular momentum conservation, its spin rate will increase by that same factor as it gets smaller. So they're spinning extremely fast, and dynamically the most likely way for matter and radiation to fall in is along the equator. It's been known since the 1960s, this is pure theory, eventually verified by observation, that a black hole with stuff around it is likely to form what's called an accretion disk. This accretion disk is, you can think of it as a disk of material with the black hole at the center, sort of shaped like a phonograph record, quite thin, extending from about 10 times the radius of the black hole. The radius of the black hole is formerly called the Schwarzschild radius, after a famous theory in the 1930s. So extending from 10 times the black hole radius to about 1,000 times the black hole radius. So this is a disk of gas and dust. And because it's moving very fast through the rapid rotation, it's swirling in a disk, and this gas is going to have a high temperature. It's a plasma of temperatures at the interior regions, that 10 times the black hole radius of maybe 100,000 Kelvin, and at the outer regions, hundreds of times the black hole radius, the temperature might only be tens of thousands of Kelvin. But these are very hot temperatures. So this gas is glowing not in the visible region, but in ultraviolet or X-rays, especially the stuff close to the black hole is going to give off X-rays. So that's just material near the black hole that's been heated up by the essentially transfer of gravitational potential energy when it started far from the black hole moving slowly to enormous amount of kinetic energy and heat or radiant heat or thermal energy when it starts moving very fast and it's close to the black hole. So that's one important way that black holes are not black. They're very often going to have an accretion disk around them, and that accretion disk is perfect for X-ray or ultraviolet telescopes to detect. And in fact, X-ray telescopes were really the first tools by which we thought that stellar mass black holes really existed. Now, something else will go on when you study the details of this process. There is a mechanism whereby the material that's bleeding off the inner edge of this accretion disk, fairly close to the black hole, and is essentially, of course, being pulled into the black hole will indeed consume some of that material. And the material that falls into the black hole is lost from the universe, lost forever. We don't see it, it's gone. And so black holes feed on the material around them, and they get larger. And that material, when it's gone, we never see it again. But if you follow the dynamics, and this is pretty complicated astrophysics that basically took supercomputers in the 1970s to work out, when that material spirals in from the inner edge of the accretion disk, some fraction of that gas and dust is accelerated in jets along the polar axes. So you have an accretion disk around the equator, material falling in, spiraling in, and then some fraction of it being shot out along opposite directed jets. These are jets of intense plasma. So it's a very rarefied but very, very high temperature gas. Now, more than tens of thousands or hundreds of thousands of degrees, this could be millions of degrees effective temperature. And that means it's shining in X-rays or even gamma rays. And so a second piece of prediction out of theory in the 1960s and 70s was that black holes should definitely have an accretion disk, and they may well, depending on the rotation pattern of the gas and dust in the disk, they may also have relativistic jets, plasma jets shot out at nearly the speed of light with incredibly high energies. And those jets have now been seen, of course, abundantly with X-ray telescopes and gamma ray telescopes. And the same thing happens with the big black holes in the center of galaxies, too. When they're feeding on gas and dust nearby, they form a huge accretion disk, and they generate huge jets that can project hundreds of thousands of light years out of the host galaxy. So those two signatures of black holes were hypothesized, actually, before they could ever be observed in the 1960s. Donald Lyndon Valley, University of Cambridge, wrote an amazing paper in 1964, 50 years ago, actually, laying out almost everything I just talked about. And it took a couple of decades for technology to catch up with that prediction, but we now have seen the indirect evidence of black holes. Remember, at the middle of all this, there's still an object, a massive compact object that is black, that we can't see inside. The event horizon is still a barrier to our knowledge. So let me just loop back to the caveat I gave, which is that in theory, in black holes, even a totally isolated in the vacuum of space black hole will actually emit a small, feeble amount of radiation. And that's a theory developed by Stephen Hawking in the mid-1970s. And the radiation that a black hole in principle should emit is called Hawking radiation, named after him. How does it work? It's kind of interesting because it's a place where quantum theory and gravity theory meet. So although nothing can escape the information membrane or one-way passage of a black hole event horizon, what we also know in physics is that out of the vacuum of space, energy can be borrowed from the vacuum to create particle and antiparticle pairs. It's called virtual pair creation. We know this happens because we've seen evidence for it in the lab and accelerators. It happens all the time because we provide the energy to make these particle-antiparticle pairs. So the vacuum of space, any vacuum in space, can create vertical particle-antiparticle pairs. And if you look at that place right near the edge of the event horizon of a black hole, then there is a probability that a virtual pair of particle-antiparticles, that could be electron-positron, proton-antiproton, neutrino-antineutrino, any pair of fundamental particles, and its antiparticle twin, there is a significant probability that that will happen at the event horizon where one member of the pair will go in and the other member will go out. Or one will be trapped forever, lost to us, and the other will emerge to be seen. And that probability can be calculated. That's what Hawking did. And what it means is that there's a small net release of either mass or energy, whichever way you want to think about it, and they're equivalent by equals mc squared anyway, from a black hole, even a completely isolated black hole. It's a fascinating result. So that's an amazing prediction. Like, have we ever observed Hawking radiation? And no, the answer is no, because if you do the math, the Hawking radiation from a black hole, such as is left behind from a massive star dying, maybe 4 times, 5 times the mass of the sun, the total amount of radiation from the event horizon gives an effective temperature to the black hole of about 1/1000th of a Kelvin. So it's fantastically cold radiation, just super long radio waves if it had thermal emission, and that's such a feeble temperature that in the crazy environment of a real black hole, essentially there's no way of us ever detecting it. So Hawking radiation is consigned at the moment to this category of very interesting theoretical ideas and predictions, 40 years old now, from the mid-1970s, that we haven't been able to test. And actually, astronomers are skeptical about whether we can ever test for Hawking radiation. Another long answer, but black holes are very cool. So I know there's a lot of interest in black holes in this course.
Okay, we have a question from Jack about telescopes on the moon. What would the possibilities of a telescope on the moon give scientists with respect to asteroid detection and understanding future detection of Earth-like worlds?
Yeah, great question, because a lot of ground-based telescope building is going on, huge telescopes And in space, their possibilities are a little more limited because it's so expensive to put telescopes in space. The James Webb Space Telescope is the next big thing, and it really might be the only big thing for the next decade because it's pushing $9 billion and counting. It's very expensive. However, for several decades, astronomers have wondered what the best place for an observatory might be. And while space is a good environment, low Earth orbit, where the Hubble Space Telescope currently resides, is not actually a great place. As you know, there's a lot of space debris, there's air glow, residual air glow, because there is a very tenuous atmosphere, even at 320 miles above the Earth, and then just below you is an atmosphere that's glowing from energy within it. And there's dust particles, there's debris from broken, satellites and meteor debris and so on. So the near-Earth environment is not actually brilliant for astronomy. Hubble's done really well, but it's not astronomers' favorite place. You probably know that telescopes have been put at the L5 point, the Lagrange point of 1.5 million kilometers, where gravity from the Earth and the Moon balance. That's a better place because that's truly dark, away from the terrestrial environment. But another place, equally good and closer, would be the dark side of the Moon, the far side of the Moon. And so astronomers have long hoped for or envisaged a lunar observatory on the far side of the Moon in perpetual darkness, shielded by the Moon from all terrestrial contamination, radio contamination, all the various emissions of the Earth, on a geologically dead world, so almost no geological noise. It's a perfect environment and a place that's not too far to get to. A place where we can send spacecraft. We do spacecraft go to the Moon, even if it's not the United States launching them every year or so. And we've had people land there, so we know we can do it. So yes, the Lunar Observatory has always been an interesting possibility for astronomy because it's incredibly dark. It's quiet for radio, so radio astronomers would love it. Optical astronomers would love it. Has no atmosphere, so X-ray, gamma-ray astronomers would love it. I mean, it's for any wavelength of astronomy you want to do, it's a brilliant location. And you could set up the infrastructure and then have it run robotically or remotely with occasional servicing missions, such as to the Hubble Space Telescope every few years. Maybe you have to send some astronauts to swap instruments, or maybe you do that robotically too. So after the initial setup time, and people have developed fairly cheap ways of robotically deploying, 3 to 5 meter mirrors, which unfold sort of the way the James Webb Space Telescope is going to unfold on the Moon's surface. And you can get your power, you can beam in your solar panel collected power and have a power source nearby. You don't need to have power. So it's a great idea. It's had its design studies, actually starting a few decades ago, and they update them occasionally. It's ready to go. And I think the astronomers' hope is that it would be a sort of not just a pan wavelength across the electromagnetic spectrum astronomical observatory. They're also hoping that the geophysicists might be interested and combine, and that it could do sort of more pan-scientific work. The price tag, hard to tell. It's going to be several $1 billion. I think the cheapest price tag I've ever seen is probably $4 or $5 billion. But that's a lot less than the James Webb. And it would do a lot more things than the James Webb, actually. So it's still a great idea. It always has been a great idea, and as you're not surprised to hear, the limitation is too many good ideas, not enough money.
Okay, so Alice Amanda asks, where do you think we will find life in the universe first?
First, good question. Well, if the Proxima Centauri system is as promising or delivers on its promise, it could be right there, 4.3 light years away. That would be extraordinary. Proxima Centauri it's actually a triple system, and 2 of the stars are Sun-like. One is a little more massive than the Sun. But they basically offer a double probability of finding Earth-like planets. They're in a binary system, but it's a binary with wide enough separation that planets around either star with Mars or closer, or 2 or 3 astronomical unit orbits or closer, would not be disturbed by the binary. So, life forms on those planets would have the kind of Tatooine issue of double sunsets and sunrises sometime. Be an interesting place to live, but there's nothing to prohibit Earth-like planets in that system. There was a false alarm, sort of a false alarm in the sense that there was a claim of a terrestrial planet around one of the stars in that system just 2 years ago, and it was not confirmed, and people are basically just looking really hard, because using the Doppler method, Earth mass is absolutely the limit you can reach, and people are not confident of their detections around there. You'd have to have got really lucky for there to be a transiting planet, and it looks like, it's unlikely that the planetary systems, if they exist in that place, happen to be aligned so exquisitely as to give us a transit, which would be much easier to observe. So people are going to have to use the Doppler method to find Earths in that system. And I think, right from 5-6 years ago when people started looking at Proxima Centauri hard, that's still by far the best bet. It is really close. That's one where if we get our 10th light speed travel of an interstellar probe, a miniaturized probe with remote sensing, we could go there. We wouldn't have to just look at it with a telescope. We could actually send a probe there that would get there in 40 or 50 years. Bit too long for my interest. I won't be around, but that kind of multi-generational mission with an enormously high potential payoff of imaging creatures on another planet. That's pretty good hook. I think that actually might get funded. Beyond the most nearby system, we're now looking at a growing number of terrestrial and habitable planets, but most are found by Kepler, and Kepler, by looking at a small region of sky and looking at pretty faint stars, is actually typically looking 100 or 200 light years away. So in Kepler's catalog, almost all the habitable Earth-like planets are I don't know of any that are, I think there's one that's about 80 or 65 light years, but most are 100, 120, 200, 300, some are even 1,000. So they're pretty far away. And that spawned a complementary project using small telescopes to look for transits around dwarf stars and nearby stars in all regions in the sky, not just the small place where Kepler has been looking. And those methods are going to take a couple of years to finish their surveys, but they're quite likely to turn up a terrestrial habitable planet within, say, 10 or 15 light years. There was actually a paper, only a couple of weeks ago, that went through all the data and calculated the most likely distance for an Earth-like planet given everything we know, and the number turns out to be 15 light years. So that's the best guess given what we know.
Here we have another question about black holes from Gabriel. How does a black hole